In this video, we will be working on a problem that involves Newton's second law of rotation, torque, and inertia. Let's go ahead and read the problem. Find the acceleration of the block and angular acceleration of the rotating uniform disk. It is frictionless at the axle, and the cord does not slip. We're given the mass of the block to be 1.2 kilograms, represented by lowercase m. The block of the disk is 2.5 kilograms, represented by capital M, and the radius of the disk is 0.20 meters. In this problem, the block is undergoing some sort of acceleration. As the block accelerates, it causes the disk to rotate and experience angular acceleration. Let's work out the details on the block. This can be set up like a free body diagram where we have two forces acting on the object, the force of gravity and tension. These two forces work against each other, and we expect a negative net force as the object will accelerate downwards. With this equation, we can't go further as the tension and acceleration are unknown. This tension force acting on the block also acts on the disk. In other words, there is a torque produced by the tension of the cord. Torque is defined as the radius by the force by sine of the angle. The tension is our force, and it is perpendicular to the radius. Perpendicular means the angle is 90 degrees, and sine 90 will give us 1. A negative sign is also attached as the torque produced will be clockwise. We're stuck here as tension is still unknown. Let's look at Newton's second law of rotation. The angular acceleration is equal to the net torque over the moment inertia, and this can be written as such: the net torque equals to the product of moment inertia and angular acceleration. The moment inertia varies based on shape, and for a disk, the moment inertia is 1/2 mr squared. Now we have net torque equals to 1/2 mass of the disk multiplied by radius squared and angular acceleration. Notice the sign of the angular acceleration is negative as the disk is rotating clockwise. There are now two equations of net torque, and they can be set equal to each other. Negative crosses out and r simplifies. We get an equation for tension, but can't use it as there are two unknowns. However, we do know the relationship between linear acceleration and angular acceleration. The linear acceleration a is equal to the radius r by the angular acceleration alpha. This can be rewritten to get angular acceleration by itself, and we can plug in linear acceleration a, or radius, r into our tension equation. Tension is now defined as 1/2 times mass times radius times linear acceleration over the radius. Radius cancels out, and we're left with tension equals to 1/2 m times linear acceleration. This equation can be used because we define tension in terms of A, and we can plug this into the equation we developed for the free body diagram. This equation looks a lot better. The only unknown in this equation is acceleration. Let's rearrange the equation to get acceleration by itself. We get mass of the block times gravity divided by mass of the block plus 1/2 mass of the disk equals to acceleration. Plug in the known variables and solve for linear acceleration. The acceleration is 4.8 meters per second squared. Afterwards, solving for angular acceleration will be much shorter, as we know that angular acceleration equals to linear acceleration divided by radius. The angular acceleration is 24 radians per second squared. Hope the breakdown of this problem was helpful. Thanks for watching.